as long as these particles are moving at all, this entropy, starting from any state, will increase both in the far past and in the far future. Okay? So it's not hard to make a theory where entropy always increases. All you do is you make a theory where there is no state of thermal equilibrium. There is no maximum entropy state. So on the one hand, that's something we would like to have be a real theory of the universe. On the other hand, this is not anywhere close to a real theory of the universe. We need to do a little bit better. There is, how am I doing on time? When do we start?
So interesting.
So interesting.
It's been 30 minutes and
oh, okay.
few seconds.
I'm going to start talking slower. Here, this is the most technical two slides that I have. I just want to sort of give you, what does this mean quantum mechanically? So this is a classical toy model that says just a demonstration. It's not hard to come up with models where entropy increases forever. What does that mean in the quantum mechanical context? Well, so here's Schrodinger's equation. The attitude I'm taking is that Schrodinger's equation is everything. There's one wave function that describes the universe, and I just need to solve it. And to make things tractable, I'm going to start by imagining there's a finite number of dimensions of Hilbert space and then make it infinite. So I can solve Schrodinger's equation perfectly in principle. This is a great feature of quantum mechanics that we don't bother telling undergraduates because in practice you can't. But in principle, quantum mechanics is the easiest theory in the world to solve. You take that state, the time-dependent Schrodinger equation being solved by some state, you decompose it as a sum over energy eigenstates, okay? These states EI, when they're hit by the Hamiltonian, there's the phase times the energy eigenstate. This is something you can always do. And then this is the solution to Schrodinger's equation. It's just that you keep the same amplitude for every energy eigenstate, but the phase evolves in a circle, and the rate at which it evolves depends on the value of the energy. Depends on omega I, which is just the frequency associated with that energy. So I can take out one of these phases, and I can rewrite it this way. And the point is that the absolutely general solution to the time-dependent Schrodinger equation is just a point moving in a torus. Okay? The torus, this n-dimensional torus, is just the torus of these phases that are describing the oscillations of every energy eigenstate. And the time it takes to go around different cycles of the torus will be different, depending on what the frequencies are. But they exist. So there's a torus of some different size along its different dimensions. And the point is that if it's finite, there's a finite number of dimensions, and you have if there's a finite dimensional Hilbert space, there's a finite dimensional torus that you're doing your evolution in, and then there's a recurrence theorem that says if you wait long enough, you're going to come back to where you started. You're going to come back arbitrarily close to where you started. So there's no beginning and end of time. All you do in forever and ever is zoom around this little torus again and again and again. The problem is, of course, that can't be our universe, because has all these Boltzmann brain type arguments. If all you do is evolve in that torus and fill it up, or if you tune things, you fill up some subspace of the torus, which is just a lower dimensional torus, but there's some space you fill up over and over again, forever, then you're most of the time in thermal equilibrium. You're going to have small fluctuations, but they'll be exponentially suppressed. All the problems with the Boltzmann brain argument are right in this scenario. So this scenario can't be correct. That can't be the real world. What do we conclude from this? That the Hilbert space of the universe is infinite dimensional, and I think this is a little bit sloppy, but it's basically right, that the energy eigenvalues can't even be discrete. They must at least bunch up somewhere, because if they were discrete energy eigenvalues, there would still be some maximum amount of time it took to go around the torus. You really want that amount of time to be infinite, otherwise the recurrence theorem will bite you. So, forgetting about this slightly technical thing, I think it's impressive that without leaving the room or doing any experiments, we're able to show that the theory of everything has the property that this Hilbert space is infinite dimensional. Okay? Otherwise, we would all be Boltzmann brains. The translation of this, both from the classical toy model and from this quantum mechanical toy model, is the universe needs to be able to grow forever and ever. And grow in some abstract sense, not the expansion of space sense, but the universe, you don't want a theory of the universe which just repeats on itself. You want it to be able to be different forever and ever and ever, if you want to explain the arrow of time. So, that's not the real world. It's still not the real world. We're creeping up on the real world slowly. So here is how I think we could try to do it a little bit better, because the problem is that our observable universe really does start in what looks like a low entropy state. So it's not just that, so it's very hard to imagine all by itself a set of degrees of freedom, whether finite or infinite, would ever look like that. The hope is that you could decompose the universe into subsystems. So one subsystem might be our observable universe, but there might be other subsystems which we don't see. And they all interact with each other not very strongly. All I mean by that is that if I know the state of one subsystem, I don't already know the state of the other subsystem. So they can evolve independently. So this is all just to make it look like science. You can divide the space of states into a product of many different subspaces, and there's a Hamiltonian which says that each subspace evolves by itself, plus there are some interactions between them. So I'm saying this because this is as far as I can go with some general framework saying what I would like out of a theory of everything. What I would like is a framework like this where it was true that in every subsystem I could increase the entropy forever and ever and sort of robustly get narrow time no matter what my initial conditions were. That's what I would really like out of a theory of everything. Instead, I have a theory of a box of gas. This is where we can actually do things. So to fix ideas, imagine that I have a box of gas, and I ask you, what is a high entropy state of this box of gas? So you'd probably guess it's something like what we have in the room. For the air, it's uniformly distributed all throughout the room. But clearly that's not the final answer, because that's ignoring the effect of gravity. If you have gravity, or if you put your box of gas on a rocket ship, Einstein tells us these are the same things, if the gravity is strong enough compared to the size of the box, then the high entropy state is not uniformly distributed through the box. It's concentrated down here. It's still a Maxwell-Boltzmann distribution inside the box. The likelihood of finding a particle in a certain energy state is still exponentially suppressed, like Maxwell and Boltzmann figured out a long time ago. But the energy is different in these two cases. With no gravity versus gravity, the energy is the momentum squared plus the gravitational potential energy, which is there or not there. So what you can imagine is some drunk person at the accelerator stick of your rocket ship, okay? And you're looking at the box of gas and you're trying to understand the entropy of the box of gas. If the acceleration is not on, the particles, we imagine they can bump into each other and they can thermalize. Okay, so no acceleration, box is there, it should fill up to uniform distribution of gas. Someone turns on the acceleration and suddenly, because you've changed the energy of all the particles without changing the configuration of anything inside the box, it is no longer in thermal equilibrium. It is no longer at a maximum entropy value. And the particles will in fact bump into each other and re-thermalize with this sort of distribution. So you have to sort of think about this for a second. What happened? I have a system here which I thought was in thermal equilibrium, and suddenly it changed to a very different looking configuration. Well, obviously it's not a closed system. You added energy to the box. So if you imagine doing this and then undoing it, so you turn the acceleration on and then turn it off, okay? It's like you're shaking the box. And you will go from this configuration to this configuration back here, but when you come back, the total energy of the box will be higher. You will heat it up, the molecules in the box. The entropy, once you turn gravity off, the entropy is basically the logarithm of the energy inside the box. So the point is that this happens over and over again. If someone's turning on the acceleration and then turning it off, no matter what you started the box in, the entropy will increase and then increase and then increase forever. It's not hard, in other words, to get narrow of time in this kind of theory. All you need is a drunk person at the accelerator of your rocket ship and an infinite amount of fuel. So you ask yourself, how can we get a drunk person at the accelerator of a rocket ship and an infinite amount of fuel? That's easy. This is what I get paid to do. So here is a Hamiltonian for a slightly more respectable theory. Now I don't have any external acceleration, but I have a field, another field besides the particles in the box. I have a gravity field. And it's not really gravity, it's not really Newtonian gravity, it's an acceleration field. So this is a field that has a momentum and it has a potential, and basically this field just rolls down its potential forever. That's what it does. Its potential just is linear or whatever, it doesn't matter. The point is it doesn't have a minimum. Okay? So if I start it here, it rolls down, and in the past it was rolling up. In the past it came from infinity, it hit a turning point, and it goes back down. Okay? That's what my field does. And then I have my particles in a box And they have their momentum, plus they have this gravitational field that they're feeling. And the gravitational field they feel depends on the value of phi, depends on the value of this auxiliary gravity field, and it goes up and down. So the natural evolution of this extra field shakes the box forever and ever. So the point of this theory is, you tell me whatever initial conditions you want. I absolutely don't care. I put particles in a box, and I give phi some value and some velocity, some phi dot. Absolutely irrespective of what those conditions are, the same thing will happen. The box will have an entropy, it will thermalize to a maximum entropy state, and then this field will shake it, and the entropy will go up. You dynamically get an arrow of time to the future and to the past, forever and ever.